All right, thank you. And thanks for coming today. Yes, I'm Kevin from the University of California, Irvine. And today I'll be talking about FELIX on behalf of the ATLAS experiment, which is a new detector readout system that we are developing. Okay, so an outline of my talk. Today I'll first give just a summary and a review of the current ATLAS trigger and data acquisition system. And then I'll talk about how that's evolving with time and how FELIX will play a part in this system. Then I'll go into detail about the different components of FELIX. And finally, I'll give a few status updates about the integration and testing program. So here is the current ATLAS trigger and data acquisition system, or TDAC. So we're colliding protons at these 40 megahertz rates at the LHC. So at the top here are our detectors, and those are forwarded to our level 1 trigger, which then with custom hardware reduces this rate down to just 100 kilohertz. Using some custom links, it's all forwarded to these readout drivers, which are detector-specific electronics built onto the front ends. And then these are processed through the readout system and eventually given to our high-level trigger farm, which does all of our high-level physics triggers. And this whole system eventually winds up in the certain permanent storage at a 1.5 kilohertz rate about. And so for the rest of the talk, I'll be talking about how we're upgrading with FELIX this rod system, essentially. So yeah, kind of as a brief review and summary of how kind of the history of TDAC. With run 1 back in 2010, we had lower rates and storing less data, and then we upgraded the system in the long shutdown a few years ago, and currently we're running run 2. And most of this talk is going to be centered on the upgrades we're planning to do in this period between run 2 and run 3, starting in the end of 2018, and for the run 3 in 2021. The upgrades for run 3, the big ones are that we're upgrading the calorimeters. I won't talk into too much detail about this, but we're upgrading the calorimeters with fine granularity liquid argon data, and also upgrading the muon system. And FELIX will be the readout system for these new detector systems. So, well, first to give a motivation of FELIX in general, I'm going to give kind of the motivation between another upgrade project at CERN. We're actually going to be upgrading the links between the detectors to these CERN gigabit transceiver links. So the links that we have now are just detector specific, and they also only flow down the chain. So we are going to have these GBT links, which are going to be able to be bidirectional and have distinct paths for the data acquisition and the slow control adapter, which can be used to control and monitor the devices. So we can send data, we can send commands up through the system from the slow control adapter and detector control system, and then we can also have a distinct path for the TTC. And we use, just kind of as a terminology later in this talk, we're called E-links to distinguish these paths. So GBT has about 40 or so E-links to separate the paths. So FELIX, a big motivation for that is it's going to be added to serve these new GBT links. So it's going to have a similar type of structure. It's going to be able to have distinct paths for many purposes, in both flow down from our data, but then also detector control and configuration that we can send up through a network on the other end, and then talk to the detectors on the other through the GBT links. So really, FELIX, it houses the GBT links on one side, and then on the other side, it just connects to a network. It acts basically as a router to the network. And So we can connect these commercial off-the-shelf components, for example, just a commercial off-the-shelf network switch to have host all the other data processing stream. So the rods, the readout drivers that is detector specific and electronics, all that type of functionality can be replaced with just standard computers. So really it's changing this to be more detector agnostic and have computers play more of a role in the readout system. And it's scalable, so we can add more links to the system as needed. Okay, so a timeline for this project. We're just finishing the last bits of our development in the end of run 2 later this year and next year. And so the LHC will be shutting down in 2019 for a couple of years. And so we're going to be integrating FELIX in with these new systems, the new muon system and the new liquid argon. And hopefully for run 4, we'll have this for all the detector systems. So kind of another picture down here on the bottom, our current system, where we have our custom electronics for our rods and only flow down from the FELIX, the front ends. And now we're going to be hoping to replace those with FELIX and computers for the readout system. So in this talk so far, I've had FELIX kind of as a black box. So now I'm going to kind of go into a little bit more detail as FELIX as sort of a system. Essentially what it is it's this computer, which is just a usual host PC running a Linux and houses a software application. And that software application talks to a FELIX card that we call it, which is a field programmable gate array, or a FPGA, based PCI Express card. And that Express card is what talks to the detectors with the GBT links and buffers the data. And then we also have a network, which connects the other side to the software application. And the network is what's used to connect to the rest of the readout drivers, the rest of the computers in the chain. Okay. So looking into a bit more detail on the card, we've developed a prototype, which we call FELIX 711. It's a 16-lane PCI Express board, which is really 2 8-lanes connected for high bandwidth, and then we can connect 48 GBT links to this prototype. We've been developing firmware for this prototype and a couple other prototypes. We have a path from the front ends on the left here. It houses through a central router, which acts as processing, and then it has a TTC channel, and then sends it on the right to the PCI Express board. And we also have paths for going from the front end boards, or from the host PCI Express board to the front end detectors. And okay, so now we'll talk a little bit about the software application. We're running a C++ application called FELIX Core. Its task is to process these data packets and forward it through, but then also to be able to handle the configuration and the commands the other direction from the network towards the on-detector front ends. So yeah, the first 2 bullet points I've already said, but also, I guess the GBTs, I said before, can be separated into E-links, and this software application has to process it quickly, so we have a multi-threaded system. So it makes subsets of the E-links and sends it on different threads. And then we have a thread about the other direction with to the front ends. And the FELIX card sends things out in 1 kilobyte blocks, and this software application has to take these blocks and put it back into the variable length data chunks. So basically the data that we're getting from the detectors will be variable length, depending on which detector is sending it, or the commands. But the PCI Express board sends it in a fixed length. So the software application recombines that to data and then sends it through the network, and also checks it for errors and things like that. And we have a low latency channel for software, for slow control adapter that I mentioned earlier. Okay, so this is just a schematic of the application. In orange is really the software part of this, which talks to the DMA buffer from the PCI Express board, and so it sends things on different threads and out through the network. And we have a TTC thread for the trigger timing and control, and we also have a host of front-end thread going the opposite direction. So the network, we've done a lot of testing of the network for FELIX. We call it NetIO. It's a message-based system. So we have a publish-subscribe system that we do in place. So the different detectors on different E-links send it to E-link 7, for example, and then any part connected to the network can read out data from that E-link if it subscribes to the E-link. We have a high throughput pattern for the data and then a low latency pattern for sending the messages and the detector control and all that. So yeah, we've done a lot of the performance testing of the network. Over here, for different message sizes, we've measured the message rate. So we're sending it at 100 kilohertz for the level 1 trigger rate, and measuring how much we actually, the peak performance we can get for the bandwidth. Messages higher than 1 kilobyte or so, we can't really have many E-links. But most for the new small wheel and stuff, it's smaller than that message size, so we are fine. Okay, so I'll just kind of wrap it up. We're undergoing now kind of the final stages of our development, and we've been able to establish some integration tests for transferring from FELIX to the network and vice versa. And we're plans to integrate with the new small wheel and the liquid argon commissioning in the long shutdown coming up. And we've also done some tests with vertical slice standalone testing, like that. And okay, so yep, thank you for coming out and listening today. The prototype system, the FELIX system is progressing well with a prototype developed and firmware and software, and we're looking forward to integrating in this to Atlas in the future. So, okay, thank you.